Welcome to AI Paper Podcasts. If you're working with LLMs, you've definitely hit that wall.
Yeah.
The context window limit. It's a constant bottleneck. Today, we're diving into a really fascinating paper that kind of sidesteps the usual scaling issues. It's called Glyph, Scaling Context Windows via Visual Text Compression. The core idea, well, instead of making LLMs handle ever longer sequences, they take long text, squash it down into images, glyphs, and let vision language models, or VLMs, handle it. It's a pretty radical shift. We think this could be a really important direction, so we want to give you the key takeaways right up front. Here's your 1-minute summary on Glyph.
Yeah, the absolute core insight is forget just adding more tokens. They increase the information density of each token by compressing text visually.
Okay, denser information. What does that actually get us?
Well, three main things. First, the compression itself is pretty impressive. We're talking 3 to 4 times token compression, while keeping performance right up there with strong models like Qwen 3 and GLM-4 on tough benchmarks like Longbench. Second big win is efficiency. Because that input sequence is shorter, everything gets faster, like up to 4.8 times faster prefilling, 4.4 times faster decoding during inference, and even training, supervised fine-tuning, gets about twice as fast.
Wow, those are serious speedups for deployment. And the third point?
The scaling potential. This is maybe the wildest part. They showed a VLM that normally handles 128,000 tokens could effectively tackle tasks needing, 1 million tokens of context just using this Glyph approach.
1 million tokens on 128K architecture.
It's a completely different angle on scaling. You sidestep the whole quadratic cost issue by shrinking the input before it hits the attention mechanism.
All right, let's dig deeper then. This context window problem, it's not new. We know why we need long context things, analyzing huge code bases, understanding long legal docs, complex reasoning tasks. They all demand it.
Absolutely. And the standard ways of getting there are just running into walls. The quadratic cost of self-attention in terms of memory and compute is brutal. Methods like Yarn, they tweak positional encoding, sure, but inference is still slow, and accuracy can really tank when you push them too far.
Right, you extrapolate too much and it falls apart. And even if you change the architecture itself, with sparse attention or linear attention, you might lessen the quadratic pain.
Yeah.
But 1 million raw tokens is still a lot of data to process.
Yeah.
The overhead doesn't just vanish.
Exactly. You haven't solved the fundamental cost issue. And that's where Glyph comes in with this visual context scaling. The paradigm shift is using the VLM's ability to handle visually dense information.
Wait, so are they just like shrinking the font and packing more words onto a virtual page? Or is there something more fundamental about how a VLM processes an image patch versus an LLM processing text tokens?
It's definitely the latter. That's the key insight. Think about what a token represents. For an LLM, it's usually a word piece, right? For a VLM, a token represents an image patch. That single visual token can capture the information from many, many text tokens. So you inherently get more bang for your buck, information-wise, with each token the VLM processes.
The paper uses that Jane Eyre example, which really clarifies it. The novel's huge, like 240,000 text tokens. A standard 128K context LLM just cuts it off, fails on big picture questions.
Yeah, that's the classic failure mode they're addressing. With Glyph, they render those 240,000 text tokens into something like 80,000 visual tokens. Now, the VLM, with its standard 128K context window, can see the whole thing.
So it can actually process the entire compressed novel.
Exactly. And it can answer those global questions like who helps Jane out after she leaves Thornfield. It gets the full picture, achieving, 3x compression in that case, without needing a bigger or fundamentally different VLM architecture.
So the sequence length the model actually sees stays manageable, even though the raw information content is massive. They're shrinking the input, making it denser.
Precisely. Smarter input, not just bigger models.
Okay, let's get into the mechanics. The paper lays out a 3-stage framework: continual pre-training, then this LLM-driven rendering search, and finally post-training. Let's start with stage 1.
Right. Continual pre-training. This is about teaching the VLM to actually read this visually compressed text effectively. The base LLM knows long context, but you need to transfer that skill to the visual modality.
And they really hammer on robustness here, using all sorts of visual styles for rendering during this pre-training. Things like standard document style, web style, dark mode, even code style, and artistic pixel. What's so much variety?
That variety is crucial. It forces the VLM to learn to extract the meaning regardless of how the text looks, different fonts, layouts, noise levels. It needs to be robust, and they use specific pre-training tasks too.
Like OCR.
Yeah, OCR tests basically, can you reconstruct the original text from the image? Also, interleaved language modeling, where the input mixes image patches and plain text, forcing the model to switch modes, and standard generation tasks, like filling in missing text.
And this whole process creates the initial glyph-based model. Got it. Before we talk about finding the best way to render, let's define that compression ratio they use. How's it calculated?
Oh, it's pretty straightforward. It's just the number of raw text tokens you start with, divided by the number of visual tokens the VLM ends up processing after rendering.
So 100K text tokens becoming 25K visual tokens is 4x compression.
Exactly. Higher ratio, more compression.
But there's a trade-off, right? You can't just compress infinitely.
Right. That ratio depends entirely on the rendering settings, things like DPI, font size, layout, line spacing. If you push it too hard, make the font tiny or the layout too dense, the VLM can't make sense of it anymore. Visual details get lost, and your accuracy tanks. It's a balancing act.
Which brings us to stage 2, and this is where I thought it got really clever. Finding that perfect balance manually seems impossible. So they use an LLM-driven genetic search.
Yeah, trying to hand-tune dozens of rendering parameters for every possible task, forget it. So they automated it with a genetic algorithm, but with a really neat twist, using another LLM in the loop.
Okay, walk me through how that LLM helps the search.
So you start with a bunch of different rendering configurations. The algorithm then repeats a cycle. 1, render some validation data with those configurations. 2, evaluate how well the model does on the task, accuracy, and what compression ratio it achieved. Then, step 3, the clever part. Feed those results, the config, the accuracy, the compression, to a separate powerful LLM. This LLM analyzes why a certain config worked well or poorly.
So it acts like a critic.
Kind of a critic and a mutation strategist. It might say, okay, this config had great compression but bad accuracy, maybe because the font size was 8. Let's try mutating it to font size 9 next time. Or, this one balanced things well, let's try a crossover with this other good one. It suggests intelligent changes for the next generation of configurations.
Using an LLM to guide the search for the optimal input representation for another model. That's pretty meta. And did this search process actually prove better than just random tries or manual guesses?
Oh, absolutely essential. The paper shows in Table 5, the configurations discovered by this LLM-guided search significantly outperformed the random ones and the ones the researchers tried designing by hand. You really need that systematic exploration to find the sweet spot.
Do they mention what the best general configuration ended up looking like?
Yeah, for their main results, the best one used parameters like a page size of about 595 by 842 pixels, a fairly low DPI of 72, font size 9, and the Verdana font family. These specifics came out of that search process.
Okay, makes sense. So stage 3 is post-training. They've got their optimized rendering configuration, let's call it theta star. Now they fine-tune the glyph-based model using this config. What techniques do they use here?
Pretty standard but effective techniques. First, supervised fine-tuning, or SFT. But they did something specific here using a thinking style format.
Thinking.
Yeah, they included explicit reasoning steps in the training data, marked with tags like think and think. The idea is to encourage the model to show its work, to perform step-by-step reasoning over the compressed visual context.
Okay, forcing it to structure its thought process.
Yeah.
And after SFT.
Then comes reinforcement learning, RL. They use GRPO, Group Relative Policy Optimization. The reward signal here is interesting. It's a mix of things.
Like what?
Well, there's a reward for just following the correct output format, rewards based on accuracy where possible, and then crucially, a reward for something they call auxiliary OCR alignment.
Auxiliary OCR alignment. Why add an explicit OCR reward here during RL? Didn't the pre-training already handle OCR?
It did. But compression always risks losing fine-grained details. Think specific numbers, names, or maybe like code snippets. By adding a reward during RL based on how well the model can reconstruct the text using Levenshtein distance as the metric they push the model to preserve that fidelity, to not just get the gist, but also the specific details embedded in the visual format. Okay, so it's an extra safeguard for preserving crucial details despite the compression. Makes sense. All right, framework, search, tuning. How did the final Glyph model actually perform against other big hitters?
The results look really strong. On long bench, it got a solid average score, competing well. On MRCR, it was often ranked first or second against models that are, frankly, much more computationally expensive to run. And this is while achieving those nice compression ratios, around 3.3x on long bench, for instance.
And what about the efficiency claims? Figure 4 in the paper has those graphs. Can you quantify those speedups again?
Yeah, they're quite dramatic. Compared to just using the text-based backbone model at a 128K sequence length, Glyph's prefill latency just getting the context loaded was up to 4.8 times faster.
Almost 5x faster loading, wow.
And decoding, generating the output tokens, was up to 4.4 times faster. Even SFT training throughput saw a consistent speed up around 2.4x. It just means cheaper, faster operations across the board for similar task performance. That efficiency angle is compelling. But you also mentioned the scaling observation, shown in Figure 5. It shows Glyph's accuracy drops off more slowly as context length increases compared to others. Why is that curve so significant?
That graph really visualizes the core benefit. When you double the raw text input length for a normal LLM, you roughly double the number of tokens it has to process, hitting that quadratic cost harder.
Right.
But with Glyph, doubling the raw text might only increase the number of visual tokens by a much smaller fraction. It keeps the actual sequence length the model sees much more contained relative to the amount of information being processed. It shows the approach scales more gracefully.
And they really pushed this scaling idea, didn't they?
Yeah.
Trying out an 8x compression setting.
They did. And even at that pretty extreme 8x compression, the model could still successfully handle tasks requiring context lengths from 128K all the way up to 1 million tokens on the MRCR benchmark. It shows there's significant headroom here for pushing context way beyond what's easily doable today.
That's incredible potential. One more check. Did this training on rendered text actually help the model deal with real-world multimodal documents, like PDFs with images and text?
Yes, and that's a great point. They tested it on long bench stock, and the Glyph-trained VLM showed clear improvements over the original VLM it was based on. So the visual understanding gain from reading compressed text actually generalized to better performance on complex real-world documents.
Okay, so summing this up, Glyph isn't just another tweak to attention. It proves that focusing on the input, making it denser via visual compression, is a totally valid, and maybe more importantly, an orthogonal approach to scaling context. It complements other methods.
Absolutely. It leverages the VLM architecture in a novel way to bypass some inherent text-based limitations. But, we should be honest about the limitations too. The paper points out it's quite sensitive to those rendering parameters.
Which is why they needed that whole complex search phase.
Exactly. It suggests getting optimal performance might require careful tuning for specific domains or tasks. Robustness isn't quite out of the box yet.
What other hurdles did they mention?
Well, OCR isn't perfect. Even with the dedicated training and alignment, recognizing really rare or complex alphanumeric strings, like, say, a unique identifier or a specific hash code within the text, can still be challenging for the VLM. There's still that tension between high compression and perfect fine-grained detail retrieval.
Okay. And task generalization.
Right. They showed great results on QA and retrieval over long documents, but they acknowledge needing more testing on really complex reasoning tasks or agentic workflows where the model needs to interact over many steps using that context.
So where does this point us for the future? If this visual compression works, what's the next step?
The paper itself hints at probably the most exciting direction, moving beyond a fixed rendering strategy. Imagine training models that learn to adaptively render the text.
Adaptively. How so?
Well, maybe the model could learn to use higher fidelity rendering for sections it deems crucial based on the query, and more aggressive compression for less relevant parts. A dynamic visualization strategy tailored on the fly. That's a fascinating thought. If a static optimized rendering gets us towards 1 million tokens, where could an adaptive, intelligent rendering system potentially take us?
It's speculative, but it could push context limits much further, maybe even towards the 10 million token range or beyond for certain tasks. It reframes the problem, not just how to read more, but how to intelligently represent vast amounts of information for AI to process efficiently. That feels like a really powerful path forward.